Greetings, physical science class. Here we are together for our exciting lecture about light. I love studying light. It fascinates me. I think that it is, next to the life sciences, one of my favorite things to study in all of science. It's unfortunate we can't be together today because I have some pretty cool labs we could have done together. But we're going to start looking at in Module 15 about light and color. And see how it has like certain rules that it follows and things like that, and then how we can manipulate it and learn some really cool stuff about it. Okay, you should have received by now your quiz for Module 14, and just take that and send it when you get a chance. Is that right? Yeah, okay. Maybe you've already done that. All right. So light, here we go. Yeah, bright stuff right there. So light acts strangely sometimes, but predictably. And the deal is we're not exactly sure how light works. Okay, so I could ask you the question: Is light a particle or is light a wave? And the answer would be yes. Okay, so we call that the dual nature of light. Light sometimes behaves like a wave and sometimes behaves like a particle. All right, so we're going to look into these two theories and see what's going on there. So the particle theory states that the light beam is like a stream of particles moving in the same direction, little packets of energy. This makes sense, doesn't it? Because remember we talked about the gravitons throwing the ball back and forth. There was little particles, little parcels of, whatever this was, gravity or in this case light, that is being exchanged, right? And so that theory is a natural progression from other things. Then we have the wave theory. That's because a light beam behaves like a transverse wave. So the transverse wave, not like sound waves, but the ones that look like waves in the ocean. All right, so sometimes they behave that way. So these are the two main theories. You need to write those two down right there, and you can pause this if you need to. Okay. Who came up with the particle theory? Well, mostly proposed by Isaac Newton as he was working with light and prisms and things like this. And he came up with that. He wrote the book called The Optics, and he came up with the corpuscular theory. But corpuscle would be like a particle, okay? So it was 1704. He looked at reflections, shadows, light traveling, shining. He also used prisms and broke light up and this kind of thing. So he said that light is like a small, compact particle of energy. He called them corpuscles, and it's flying through a void. In fact, it could go through a vacuum. All right, so that's Newton. And then along comes this guy, Christian Huygens, who did some work with light. He built upon what Newton had taught. And he said, wait a minute, sometimes it doesn't act like that particle. So we came up with what is known as the wave theory. It transfers energy without transferring matter. In other words, like a wave will bring something in, right? Like a wave of the ocean. These waves is going through something, and so traveling through it without bringing matter in. Because remember, light is not matter. It doesn't take up space or have any mass. So it's got its kind of unique place in physics. He said that light waves have various wavelengths, frequencies, speeds, and amplitudes, and all of those different things will affect the way light looks, the way that it acts. And so that's why he said it must be a wave. So he did things like this. For instance, if light is a particle, all right, then it would be coming out from a source, and when it hits a barrier, it would just be stopped right there, okay? But what Huygens noticed was sometimes they bent this way, like this, which acted more like the ripples of a wave. It sort of bent past the barrier. And the particle theory didn't quite explain that, which is why Huygens came up with his idea. Let's watch a little video to give us a little more insight.
You look down and see a yellow pencil lying on your desk. Your eyes, and then your brain, are collecting all sorts of information about the pencil. Its size, colour, shape, distance, and more. But how exactly does this happen? The ancient Greeks were the first to think more or less scientifically about what light is and how vision works. Some Greek philosophers, including Plato and Pythagoras, thought that light originated in our eyes and that vision happened when little invisible probes were sent to gather information about faraway objects. It took over 1,000 years before the Arab scientist Al-Hasan figured out that the old Greek theory of light couldn't be right. In Al-Hasan's picture, your eyes don't send out invisible intelligence-gathering probes. They simply collect the light that falls into them. Al-Hasan's theory accounts for a fact that the Greeks couldn't easily explain: why it gets dark sometimes. The idea is that very few objects actually emit their own light. The special light-emitting objects, like the sun or a light bulb, are known as sources of light. Most of the things we see, like that pencil on your desk, are simply reflecting light from a source, rather than producing their own. So, when you look at your pencil, the light that hits your eye actually originated at the sun and has travelled millions of miles across empty space before bouncing off the pencil and into your eye. Which is pretty cool when you think about it. But what exactly is the stuff that's emitted from the sun, and how do we see it? Is it a particle, like atoms? Or is it a wave, like ripples on the surface of a pond? Scientists in the modern era would spend a couple of hundred years figuring out the answer to this question. Isaac Newton was one of the earliest. Newton believed that light is made up of tiny, atom-like particles which he called corpuscles. Using this assumption, he was able to explain some properties of light. For example, refraction, which is how a beam of light appears to bend as it passes from air into water. But in science, even geniuses sometimes get things wrong. In the 19th century, long after Newton died, scientists did a series of experiments that clearly showed that light can't be made up of tiny atom-like particles. For one thing, two beams of light that cross paths don't interact with each other at all. If light were made of tiny solid balls, then you would expect that some of the particles from beam A would crash into some of the particles from beam B. If that happened, the two particles involved in the collision would off in random directions. But that doesn't happen. The beams of light pass right through each other, as you can check for yourself with two laser pointers and some chalk dust. For another thing, light makes interference patterns. Interference patterns are the complicated undulations that happen when two wave patterns occupy the same space. They can be seen when two objects disturb the surface of a still pond. And also, when light acts like a wave, leads naturally to an explanation of what colour is, and why that pencil looks yellow. So, it's settled then. Light is a wave, right? Not so fast. In the 20th century, scientists did experiments that appeared to show light acting like a particle. For instance, when you shine light on a metal, the light transfers its energy to the atoms in the metal in discrete packets, called quanta. But we can't just forget about properties like interference either, so these quanta of light aren't at all like the tiny hard spheres Newton imagined. This results that light sometimes behaves like a particle, and sometimes behaves like a wave, led to a revolutionary new physics theory called quantum mechanics. So, after all that, let's go back to the question, what is light? Well, light isn't really like anything we're used to dealing with in our everyday lives. Sometimes it behaves like a particle, and other times it behaves like a wave, but it isn't exactly like either.
Alright, does that help? Does that explain things to you? And really the answer is, we don't know. Alright. If light is a wave, through what medium does it oscillate? Remember we talked about waves going through a medium with our sound thing right there. James Clerk Maxwell discovered that light travels like an oscillating electric field with a magnetic field oscillating perpendicular to it. Wow. Okay, so James Clerk Maxwell is one of the most brilliant people out there. I think we've talked about him already, right? Very brilliant. And here's what he was thinking, okay, his conclusion, that these are what electromagnetic waves are. Okay, so light's made up of two perpendicular waves. One, so I try to see this in three dimensions. This one's coming straight out at us, and this one's going straight up. Okay, so out and up. So they're 90 degree angle right here. So the second wave is oscillating magnetic field. All right, so we have electric field going up, magnetic field coming out together. They're perpendicular to each other and to the direction of the light traveling. This little thing should be right there. Therefore, they're called electromagnetic waves. So for Maxwell to bring this together into the electromagnetic waves, which we know about, is pretty fascinating that light is now going to be a part of that. Now, it seems reasonable that God's design would have everything just fitting so beautifully together this way. Because we think that maybe even gravity is put into this deal, right? In the video, it talked about the photoelectric effect. This is where we ended up thinking that light actually could be particles. So in other words, Newton wasn't wrong, he just wasn't all the way right, okay? And I think we're still not all the way right. What happened is you take a piece of metal, this one happens to be sodium, you shine light onto it, and some of the little pieces of sodium will be kicked off. Okay, they'll actually be shot off of light, like something hit it and knocked it off. And therefore that seems like a little bullet of light hit it and knocked it off, exactly what Newton would have said. All right, but yet we know that it has that interference pattern like drops in a pond where you leave the little ripples, and those ripples hit each other and have that interference there. So we can't forget about that. So now what we're kind of going with is this quantum idea, which is the idea that it's a particle wave. Okay, so look, this is the particle, and it's a wave. So our particle or wave, and the answer is yes, that's what it is. Okay, all right. That brings us to the quantum mechanical theory of light. Light is viewed as packets of waves, not exactly continuous, but sometimes acting continuously. All right, so here's our light bulb. Sometimes those are coming out like a wave continuously, sometimes like a stream of particles. And that's about as good as I can do right now. I'm not a quantum physicist. That's about as much as I can handle in my brain. So, the best of our understanding, we believe that light travels in little packets of waves. Each packet can be thought of as a particle called a photon. That's what that little thing is called, a photon. Just like a graviton, this kind of thing, a photon makes sense. At the same time, the packet is also composed of electromagnetic waves, according to James Clerk Maxwell. So this picture right down here is actually showing a very famous experiment where we are sending light through these little slits in a screen. And if they were particles, they would have just made these little things right here, these two blanks right here. But they ended up making other parts of light around on this side right here, which made it look like it was coming out like a wave, like disturbing the water like a wave. So this was a famous experiment, which is why we can't just ignore that part of it. Okay, so we have to try to fit all that data in to the best of our knowledge. Someday in heaven, God will say, here's how it's done. And of course, our minds at that point will say, aha, we'll understand all that math then, right? I sure hope so. Although I hope there's no math in heaven. Okay, some things that we do know about light, even though if we're not sure exactly how it emanates, we can certainly test it and see how it behaves. It behaves very predictably, okay? So we can look at, for one thing, the speed of light. Now, it's very fast. Typically, we say it's 186,000 miles per second. 186,000 miles per second. That's the same as 670,616,629 miles per hour. And we see the rest of them over here, meters per second down there. That's fast. It's very fast. And furthermore, it's what we call a constant. So as far as we know, it is not changed. It doesn't change. Okay, so it's constant. Furthermore, it can go through a vacuum. That means it can come through space, which is fortunate, seeing as how the light from the sun needs to get through us, and the space doesn't have a medium through which to travel. Remember, sound can't get to us from the sun, but light can. So it's a miracle. It's a good thing. It does travel through different things. I'm not sure if you can read the top of this up here, but we're looking at the way it propagates over a distance through different media. Okay, so through empty space right here, all right, going through space, which is essentially a vacuum, it travels its fastest right there. So there's that number, 299,792 kilometers per second. That's 100% of c. C represents the speed of light. Okay, keep that in mind. All right, to go through air, it slows down a little bit. Not much, but it does slow down a little bit, 99.97. Through water that's fairly dense, it's going to pass through that even slower, about 75% of c, which is, this number. Through glass, it'll slow down to 65%, and then through diamond, it'll really slow down to 41. Now, it's still traveling 124,000 kilometers per second. So that's still very fast. Now, they have been doing some work with this where they'll take something like a diamond or something, diamond is the hardest substance, right, on Earth. But if they get it really, really, really cold, they have started seeing where they can slow down light enough where you can kind of watch it. You know how if you're trying to like download something on your computer, maybe in the old days, and you'd see that little bar filling up like that? That's how I saw a program that showed that light moving like that, still pretty quickly, but I could watch it. So that definitely slowed it down. And they had something very dense like diamond, and it was very, very cold, which really slowed it down. So cool, it'd be interesting to see. There's also a little bit of evidence out there to show that this right here is actually slowing down a little bit over time. That would also make sense according to the second law of thermodynamics, which states that all things are subject to the law of increasing entropy. Everything's slowing down just a bit, right? So that'd be interesting. All right, here's Albert Einstein. And he is working with, at this point, he was working with the idea of the dual theory of light, trying to figure those things out. And it brought him to an interesting conclusion. And that conclusion is a famous theory called the special theory of relativity. It states that nothing can go faster than the speed of light. It's the ultimate speed limit. We're talking at roughly that number right there, meters per second, 300 million meters per second. Is that number right? Okay. So that's the ultimate speed limit. Does light travel in a vacuum? I believe this is in your book. You need to answer this. Absolutely. Thank goodness it does. So that's the answer to that question. Does light travel faster in a solid or a gas? You should know that from looking at that previous slide we saw. Which one is it? It's a gas. Remember, that was different for sound, right? Does light travel faster in a liquid or a gas? It's also going to be a gas. It's going to travel the fastest through that, which is also, again, fortunate for us. So when the light of the sun comes into our atmosphere, you know, it's pretty much undaunted, right? It's not easily stopped there. Okay, so this is a little video we're going to watch about relativity. So when we take that light and think about that light, Einstein used that and took it to some weird kind of conclusions about light traveling and how it affects us and how it affects time. He put all those things together and came up with his most famous mathematical equation. Let's see.
Time. You can't see it. You can't hear it. You can't weigh it. But we experience it every moment. The whole piece of time is a landscape, and we move through it, slice by slice. But do we really understand time? Is time same for everyone? To understand time, let's go back in time and make a small journey with a certain young patent clerk, Albert Einstein. Imagine you're traveling with Einstein in a train moving at a certain uniform speed. The train, relative to the outside environment, is in motion. The two of you sitting inside, on the other hand, observe each other as stationary objects, as both you and the train are moving at the same speed. Hence, relative to the train, you are stationary, and the laws of physics stay same inside the train as they would on the ground when you are standing still. Now, let's consider you get off the train and observe it moving across in front of you. Now, you are stationary, and relative to you, Einstein is moving with the same speed as the train. This is the phenomenon of relative motion, and we observe it every day. Does everything in the universe observe this relative motion the same way? Yes, everything except light. Light behaves in a different way. Imagine you have a light clock with you. This light clock has two mirrors in the opposite directions and a light beam bouncing between them. Now, let's say the distance between the two mirrors is d, and the time for the light to cover that distance is t. For the sake of simplicity, let's say it's 1 second. So, when this clock is with you at rest position, the light bounces between the mirrors, covering distance d in 1 second, which gives us the speed of light s. Now remember, speed is distance per unit time. Now Now consider Einstein also possesses the same light clock with him. Only this time, he's traveling in a spaceship along with the clock. When Einstein travels in a certain speed, the clock travels with the same speed of the spaceship in the same direction. Here, light has to travel an extra distance in the same 1 second. Let's consider this distance to be capital D and represent the speed of light here as capital S, which has to be greater than small s. But something's wrong here. Because in the late 1800s, the Michelson-Morley experiment tried to detect the relative motion of the matter through an ether and concluded that the speed of light is constant. This cosmic speed limit is known as c. So in our little scenario, small s and capital S are equal. So for the speed of light for both you and Einstein to remain constant, something has to give way. That something is time. It turns out, time slows down when you travel faster and faster, nearing the speed of light. So the faster Einstein travels, slower the time passes for him. Hence, what could be a day for Einstein in space could be as much as 50 years for you on the ground. This became the fundamental conclusion of the theory of relativity, a theory proposed by Albert Einstein in 1905. This theory broke the traditional understanding of time as a constant entity and proved that time, in fact, is different for different observers. The theory of relativity led to many other invaluable findings, the most famous of which is the equation E equals mc squared. But more on that later.
All right, so did that help you at all? Yeah, it's kind of interesting, kind of weird, that idea of his, that time and... So E is energy equals M, which is matter, mass, right? And c squared, which is light, the speed of light. So that's time. You see, so they're all related to each other there. Very interesting. Okay, something that's a little more apprehendable right here is the idea of what we do know about light, what we can experiment with light for. So what we do know is that there are different wavelengths, so therefore this is going to play into what Christian Huygens was saying, that if we have if it's traveling as a wave, then we have different wavelengths, right? And those different wavelengths are manifested or made are different from one another depending on how they look, how they act, okay? So, for instance, if we're looking at the wavelengths right here between 400 and 700, it turns out this right here is called the electromagnetic spectrum. It's everything. Okay, we could get down here and find some, I'll get to another picture in a minute to show that, which you will need to draw in your book. But between these two wavelengths right here is what is known as visible light. Okay, it's the stuff we can see. And because we can see, though, those are actually broken into their representative colors. Red, orange, yellow, green, blue, indigo, violet. We call that Roy G. Biv. R-O-Y-G-B-I-V. Roy G. Biv. Okay. Anything that's beyond violet would be ultraviolet. If we keep going this way, we would get to the shorter wavelengths. So these are shorter. See, 400 is shorter than 700. Shorter wavelengths. Those wavelengths become X-rays. And then we get over here these, crazy things like gamma rays. As we move this way, those short wavelengths become very powerful and they can cause damage to our cells, including X-rays, which we'll get to. All right, so anything beyond violet is ultraviolet. Anything beyond red is infrared, okay? On this one, we cannot see anything over here anymore. Our wavelengths are getting longer and longer. We move this way down the spectrum, we're going to see things like radio waves, microwaves, things like this. Now, to show this visible light spectrum, one thing that Isaac Newton did, we were supposed to do today, was to look at the spectrum. Here we go with our 400 to 700, red, orange, yellow, green, blue, indigo, violet, right there. Here's our shorter wavelength. Here's our longer wavelength. You can see those wavelengths right there. Okay, getting really short. These get, see, gamma rays, X-rays, they become damaging. So is ultraviolet, UV light, right? Here's our visible light. Look, it's a very tiny little sliver right there of the spectrum. Infrared, radio waves, TV, I think microwaves over there. I think so. And here it is. There's our Roy G. Biv right there. So what has the longest wavelength of the visible light spectrum? Red. What has the shortest? Violet. Okay, that's probably a real good quiz question. So know that red, if red is the longest and violet is the shortest, if I asked you which one has a shorter wavelength, blue or orange, you should be able to tell me that. Okay. Now, this I believe you're supposed to write down in your book. Let's see, you were supposed to draw a light wave earlier. And now you're supposed to, I think it says draw the rainbow here. I think you're supposed to draw, oh no, here we go. Draw the electromagnetic spectrum. Okay, so the rainbow you're going to do Roy G. Biv right there in your book, okay? In that, if you had colors, that'd be awesome. If not, just write the words, okay, and show how the rainbow goes that way. That's why a rainbow is that way, because it's just a spectrum broken up, light's broken up through the little prisms, the prismatic action of raindrops, okay? So, but this is the whole electromagnetic spectrum that we know of, okay? So think about it. We're talking about a light wave, yes, okay? But we're also talking about radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, all of these things, okay? Remember what Maxwell said, that these things are really electricity and magnetism in an electromagnetic wave. So the whole thing is known as the electromagnetic spectrum. It's really quite fascinating, and it's amazing that God has such order in this, right? It doesn't have a whole bunch of different things that he's throwing in. He's got this same thing, and they're manifested in different ways. For instance, in this right here, we can see it. Very cool. This one, by the way, is turned around from the previous ones. Here's our shorter wavelengths here and our longer wavelengths there. I like it because it does go in the order Roy G. Biv right there. But also, so we're going to see our lower frequency, longer wavelengths here. Radio. So radio waves are flying around us right now. I happen to have a radio with me, and I would turn it on, and you could hear something on the radio, right? It's just picking up those waves and then taking it. It's like a miniature brain, if you will, that takes the waves that are already in the air, and then it transposes it into the sound that I can hear. But the radio is coming from a tower somewhere in Austin. There's a radio station that's sending out a signal, and when that signal hits my radio at the right frequency, that's when I tune it to the frequency. So like 590 AM is my talk radio show. And I put it on right there, and at that frequency I can catch whatever frequency they're sending the sound out on. Pretty cool, huh? Pretty low tech, but also quite scientific at the same time. All right, then we get to a little bit longer. I mean, it's getting a little bit faster here, right? Closer together, increased frequency here. And this is a microwave, okay? So microwaves are all around us too, but we can take those and concentrate those, and we do in something called a microwave oven, and it is the same thing right there. All right, we're speeding up a little bit more, and we have now our infrared. We'll talk about, remember, we can't see this right here, but we can actually figure it out by, it actually lets off heat, and we can actually see the heat with special glasses. Then we have our visible right here, teeny tiny part of the spectrum right there. That's all we see, right? Here, I guess they're telling us here the size of the wavelength. They're huge at this point. Then they get much smaller. Eye of a needle. Here it's something microscopic. Here, you know, very small. Viruses are the tiniest things we know. Protein, the parts of the proteins, not the actual whole protein, but the parts of the amino acids right there. Atoms and atomic nucleus right there. All right, so hold on. Okay, then we get to faster wavelengths here. We have the ultraviolet that are about this size, remember, of amino acids. And these are getting a little more damaging here, UV. We'll spend a lot of time on that today. And then we get to the X-rays, which are very damaging. And then the gamma rays, which are deadly, okay, because they're like little bullets being shot at us right there. So therefore, those are probably the ones that are acting a lot like packets. Okay, so here it is. You're going to draw the electromagnetic spectrum, shown on page 372 of your textbook. I believe that's right. This one's a simple one. If you want to draw this one in your lab book, that would be fine. Okay, so go for that. You can pause this and draw that in your book there. Okay. All right. X-rays, they're very useful for us, okay, because what we can do is we can actually see things that we wouldn't normally see, So like right here, we're looking through the skin into your body at the X-ray of somebody's hands, right here. And so the things that are made of dense material, bone, are more visible than the things made of less dense material, skin and muscle. And so you can see this will be very helpful if somebody has a break or something, that we can diagnose that. Now, but X-rays do have inherently damaging qualities to them. So now when I was working my way through college, I was working at a veterinary clinic, taking care of different animals for different reasons. And one of the things we did, and one of the things I was in charge of, was X-rays. So I took X-rays of all sorts of critters. They would have, get hit by a car and have a broken leg, or they would maybe have a foreign body in their stomach or something like this. And so I always took them into the X-ray room and had to measure them and stuff. And I would wear an apron made of lead. It was very heavy, and I would put it over myself and strap it to myself so that my cells were not getting exposed to a lot of radiation. Meanwhile, I also had to wear this special little badge, and I wore it kind of clipped to my collar of my shirt, and when I put my apron on, the little tab would stick out. And so what it did was it registered every bit of X-ray rays that were going into me through the X-rays. And every 6 months or so, or maybe it was 4 months, they would send those in and give me a new one, and they would check it to make sure I wasn't getting exposed to too much radiation. And so I didn't ever get exposed to too much radiation. But that was a way of testing it. So in other words, we need to make sure you don't get exposed to too much. This is infrared light. So I told you it kind of measures the heat that's put out. So we couldn't see this. Like, we could see the elephant, of course, but we couldn't see its heat. And so if you look at them there, the warmer parts of the body are kind of red and the cooler parts are blue. So it looks like the tip of the ears here are kind of blue. This is what gives us the idea that elephants' big ears are to help with keeping the critter cool, to cool them off a little bit. In fact, they flap their ears and things like that. A lot of blood vessels up there that help cool the blood down. And it's part of their system to keep their body temperature the same. Yeah, I don't know what's happening right over here. Something's glowing right there. Of course, we use infrared light glasses, so night vision goggles, that kind of thing, to see things that still emanate heat, but they're in the dark. So we could see this elephant in the dark with these particular lights on, glasses on, right? And so police officers and things, they use that kind of thing for finding, bad guys. Microwave, so you can see those waves are in there. What happens, the way a microwave works is that these low frequency waves come in through here. They're generated inside a special, wave generator, and they generate through here. And what they will do is the food that's in there has water, and water, H2O, has polar qualities. In other words, one side slightly positive and one side slightly negative. And what will happen is when the microwaves hit them, it'll cause them to start spinning around. It's almost like a magnet is hitting them and causing them to spin around. When they start to spin around, guess what they do? They create friction, and that friction heats things up. Now this will cause that heat to cook the food. Now you may have noticed sometimes some types of food are don't heat as well in microwave. If you think like a piece of bread, you put a piece of bread in there. Well, think about it. There's not that much water available in the bread, and furthermore, you put it in there and the water comes out of the bread because a little bit of it's going to evaporate, right? And so when that happens, when it takes the moisture out of the bread, it dries the bread out. So if you leave a piece of bread in there very long, it kind of gets hard and chewy and that kind of thing. So you don't want to heat up bread in a microwave. And it just has to do with the water content. Okay, now some other principles of light that we can easily apprehend is the concept of reflection. So we've been talking about reflection and refraction today. And I think next week we'll talk more about refraction. It's a little different than reflection. Okay, reflection, here is the definition we're going to have for it right here, is when a light wave bounces off an obstacle and it bounces back. typically the thing would be shiny, so it reflects well. So you could say if I shine a light on a mirror, it's going to reflect right back at me, right? Because a mirror is a very reflective surface. If I shine a flashlight against a plain wall, some of it will bounce back at me, right? But not quite as well. But it will help to kind of move that light around a little bit, sort of spread it throughout the room or something. So some things are reflective and some things are not. A mirror obviously is very reflective. Look at those beautiful swans. I'm thinking that must be not real, right? Somebody must have manipulated that picture, but you can see them reflected in the water there. So the reflection, how does it work? Well, it works based on some rules. Okay, it follows rules. I will say that about light. It tends to follow rules. And one of those rules is called the law of reflection. So it turns out when I shine the light into a mirror like this, it's going to hit it at a particular angle. And whatever that angle is, it's going to reflect up there. So this is called the incident ray. It's going to come in and hit, and then it's going to come like this. So this angle of incidence based on, so this make-believe middle line right here, this angle of incidence from here to here will equal the angle of reflection, okay? So if I move this, this will move. All right, that seems to probably seem intuitive there. And in our lab today, I'll show you that how that works a little bit. I'll show you how the incidence comes in and the reflection goes out. Okay, so that's a law, yeah. So when you see reflections, this always kind of has fascinated me, is that if you're looking into a mirror, okay, let's think about it. We must have light, first of all, to see anything. If it's dark, we're not seeing anything. That makes sense, right? Next week, we'll talk about how that refers to color. In reflection, light bounces off an image, say me, okay? It hits a mirror and reflects off the mirror and then goes into my eye, so I can see myself in the mirror. Our brain will interpret that light traveling in a straight line, because light travels in straight lines, okay? Light coming in, bouncing back, hitting here, okay? And then I'm looking at my mirror reflection like this in a straight line, straight line, straight line. So if you think about this, we call this a virtual image. Think about it. You're standing in the mirror in the morning brushing your teeth, right? Look in the mirror, and I need you to see that your virtual image is actually behind the mirror. Does that make sense to you? All right, so you think, what do you mean it's behind the mirror? There's nothing behind the mirror. There's a wall behind the mirror. Well, but look where you are in relation to yourself. So let's say there's a sink between you and the mirror, right? So when you look in the mirror, is the sink there too? Sure, right? So you're still behind the sink in the mirror. So you're that far back. Do you get it? It's a virtual image. It's kind of like it's tricking our eyes a little bit. Pretty cool, huh? Kind of blows me away a little bit. So that's that virtual image. Okay, so we have some experiments. You have some in your book. And furthermore, in the ones that are listed in your book, you can do these at home. They're pretty easy to do. First thing you're going to do is to see some of the different wavelengths by casting a rainbow, by making a rainbow. So there are various things you could use for that. I will say an old CD or something will, if you shine the light just right, you will see the little rainbow reflected in that, yes. If you shine a flashlight on it, you can sometimes cast a rainbow with that. But the experiment in your book, however, talks about taking a small mirror, if you got a small mirror, put it into a dish of water, and then put that water, that whole dish, the whole pan, at the sunlight. The sun will bounce against the mirror and through the water, and you can sometimes make a rainbow that way. Another way to do it is if you go outside on a sunny day and take a hose and spray a very fine spray out of the hose, you can see a little rainbow in the hose there, okay? So try that, okay? Especially on a hot day. We've had some hot days. You can do that and see a little rainbow. You probably know exactly what I'm talking about. If you've ever washed the car or something like that, you can see that cool rainbow there. Okay, the experiment 15.2 is to look at making, what you're going to do is show that angle coming in, okay? Show the angle of incidence equaling that other angle coming out, the angle of reflection. And it is on page 374, 375. It's a little more elaborate. You have to take and cut a little slit, but the stuff I have that I'll show you in our lab already has that. So if you just watch that thoroughly, that should take care of the situation there as far as doing that lab. The other thing was hitting a target using reflection. This is one of the reasons I'm sad that we're not together, and that is because we were going to use laser lights, laser pointers, and we would, bounce them and try to hit a target. So, sorry, Maybe you have one of those at home. All right, so we're going to do my version here of the experiment 15.1. Let's see what I got. Okay, so we're going to start the lab now. All right, hi. This is the light lab, and it disappoints me that I'm not there with you to do this because it's just a ton of fun. All right, so the first thing we're going to talk about is this. It's a prism. All right, so I have several of these, and I would have had you hold these up. And what you do is you're going to take them, and we put them into the sunlight, and as we direct the sunlight through them, it will actually split the light up and then cast a rainbow. So we call it throwing rainbows, and we could throw rainbows over the wall, presuming that there was sun coming in those little slits of windows in our classroom. And we would have done that, okay? So, but this does change the way the light, reflects through there, or refracts would be the better way of saying it, and causing it to split up into its spectra. All right, since we're not there together to do this today, I did send home something with you, and it looks like this, okay? So what this is a little screen that has been treated in such a way. It's sort of like a plastic screen with little lines in it, and those lines actually create prisms. And in particular, this one I sent home with you because it's the most impressive, has, it says right on there, 13,500 lines per inch. Okay, I have a 500 and I have a 1,000, but I had enough of these to send one home with all of you, plus one left for me. And so you're going to see on the bottom right here, you can see where it has the wavelengths right there, right? Okay. And what I want you to do with this, I want you to take this, and I want you to look at an incandescent light bulb. So just light bulb in your house, just like this. And you should, and move it around like this. And what you should see is the light bulb is kind of split up, and I want you to look really closely to tell me if you see all the colors of the rainbow. Okay, so red, orange, yellow, green, blue, indigo, violet. Okay, so take a look, see if you do that. Now I want you to take that and aim it out of a window and see if there's a change. All right, so I'm aiming it out my window right here. I think it works best when you hold it right up to your eye. But if you want to hold it out like this to see it, it definitely works better this way. All right, so you can see there's like a little difference because we have diffuse light out there with the sun. Never, of course, look directly at the sun. You know this, right? Don't do it, all right? So, but what we're seeing here is that the prism is showing us that spectrum. Okay, so the spectrum. We would work with those. And then the other thing I have is this really cool deal. It's called a spectrometer, all right? It has a little hole, right? You almost saw it there, right there, that you look through, okay? And you take and you look up this way, like this, and you shine it at the incandescent light bulb, and you're going to see the spectrum being cast across on this side. So you see there's a little slit here, and I don't know if you can tell that. All right, there's a little slit. The light comes in right there. And then over here you can see there's a little screen. So what happens is the light comes in, and we see it on this little screen coming in. We see the light like this, and then I can see a beautiful, beautiful spectrum right there. And I'm looking at an incandescent light bulb. I already took it outside as well to see about making a picture of it. If you look out in the sun, it looks a little different in the sun, okay? So it's kind of diffuse right there, and you can see it. I tried to take a picture. I'll see if it worked. And I'm going to try to take a picture of this right now, all right? So this would be our lab today, plus we're going to work a little bit with reflection in just a minute. Okay, I'll be right back. Okay. So here's the prism. So I took the prism and I held it up to the window right there on a sunny day. And you can see I threw a little rainbow on the ground there on my floor. And so we would have been throwing them all over the walls at the church over there. And if we didn't have sun coming through that window, we would have gone outside and done it. Presuming it would be a sunny day, yeah. All right, so here, I actually took these pictures through my little spectroscope. Okay, so this is the one from the house. Yeah, so this is using incandescent light bulb in my kitchen. You can see red, orange, yellow, green. Well, they're really cast around there, aren't they? This is the sunshine one coming in. All right, they're separated a little bit because it's pretty bright, obviously, coming in there. So a little different, but see how they're all kind of they're pushed together this way. So they're similarly pushed together this way. All right. But the really cool thing is when you take it and put it up to the fluorescent light in the room, in the schoolroom. I don't have any fluorescent light at my house, so I have incandescent, I have sunlight, which are real similar, but when you look at the, I have a picture here from the internet, this is what the spectroscope looks like for fluorescent light. Look at that. Yeah, so they're completely separated. And look at that. Notice how that blue is always on the other side there. That's pretty cool. Our purple's over there, yeah. All right, so it would have been fun for y'all to be able to look through these spectroscopes, and it kind of takes a little time to get used to them. We would have had to share them, of course, and that kind of thing. So it would have taken us a good time to finish that lab. Okay, now we're going to look at the law of reflection. I have this really cool kit called the Tech Light Lab. All right, and what I have these little flashlights, and for instance, this is the blue one. You can see here the blue one, and I have a green one. We're going to use these next week for sure, the green one. And then I have a red one like this, but what I have on there is it's got this little fancy cap to it right here that has a slit through it, okay? So therefore, on my red one, I'll show you here, see, it makes a slit of light. You can see it on me right there, yeah. And what I'll do with that, oh, I'm shining at me, duh, okay. So, there we go. See that slit of light right there. All right, so what I'm going to do is I'm going to shine it into a mirror, and we're going to see some reflective quality of the mirror, okay, and how it reflects that, okay? So I have a picture of it because it's dark enough down here. I have it on a little thing like this to show you about the angles that it's doing that. Okay, so we're looking at light and reflection. Next time when we're together, we'll look at the colors, okay? So we're going to take these three colors and we're going to do some cool stuff with it. Today we were just doing the reflection thing. All right, so I'll show you those pictures in a minute. Great. Okay, so here they are. So you can see I have that flashlight coming in. It's kind of hard to tell. I think it was at 120. Does that say 120? So it's going in. Here's my midpoint right here. So it's the line of incidence and then the line of reflection. And notice it's exactly the same going in as it is coming out. I moved it to a different location. Look, going in at 120, coming out at 120. Did I say 120 here? Maybe that's 150. I just can't tell. I can't see it closely enough. All right, so we would have turned the lights off in the room and done this, and y'all could have seen how we, move those around like that. Okay, which the thing that really disappoints me more than anything, however, is lasers. Okay, yeah, that's fun right there. So the way that a laser works, like a laser pointer, now, these were developed, I think, in the 1970s. And what we have is we have a laser medium in here. Typically, it's some sort of gemstone. A ruby is often used, which is why the laser beam ends up being red, because the ruby's red. And we have some mirrors and partial mirror right here. And what happens is that the electricity will excite the laser medium, so I have to have a battery or electricity of some sort, and it will start bouncing back and forth, back and forth, back and forth between these two mirrors until it makes it out of a little hole right here with my little laser beam. Now, depending on what that laser medium is going to be the color of the laser coming out. So typically, red is most common, but I have a blue one and a green one as well of those. Okay, so we would have taken those and shine them in a mirror to another mirror to hit a target. Okay, it can actually be a little tougher than it looks right there. I got this inspiration from a game my boys had, that they had to take that laser through a little game board to hit a certain target or something like that. Yeah, so pretty cool. The biggest problem I have with using the lasers in class is that sometimes y'all get a little rambunctious with them, you students, and end up shining them at people's faces. And we want to keep that from happening. While laser pointers are not the strongest lasers obviously out there, there are some lasers that are strong enough that they can, cut metal. So they're very, very strong. Not a laser pointer, but it isn't great to have it pointed at your eye. It can go in there, and if it were concentrated enough, it could burn a little patch of your retina, and your retina then would be damaged forever in that spot. So we want to avoid something like that. So be careful with using a laser to reflect. So if you want to if you have a laser pointer, which is probably not out of the question, you probably may have one of those, you can try doing some reflecting experiments at home. Just remember, if you're looking in a mirror and you shine it in a mirror, you could accidentally end up shining it in your own eye. Okay, so let's avoid doing that kind of thing. All right. Okay, so just regular homework. Do your as you're reading your OIOs, do in your head or whatever. But remember, for me, the study guide will work. All right. Next week is a ton of fun because we'll be looking at color and how color and light are absolutely part of the same deal. Okay. All right, guys. See y'all soon.